Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we are going to get really close to finishing Chapter 5, and we'll be discussing today, or in this video, Unbalanced Two-factor Analysis, Types 1 and 3 Sums of Squares, and we'll discuss all of that in the context of an example about rat insulin. So, as we've mentioned before, a balanced design is one for which the sample sizes for every treatment combination is the same. And unbalanced is when we have different sample sizes. That unbalanced design might happen accidentally if you've allocated your observational units equally and then something bad happens for some of your observational units that you can't collect data. For example, you are conducting experiments on rats and you accidentally kill some, and then you don't get to take those measurements later. That would be a situation where you end up with an unbalanced design. Sometimes you don't have the liberty to do randomization, but you are simply observing something, so sort of like an observational study, but where everything's sort of randomized or pseudo-randomized in a way that leads you to unequal sample sizes. So that would be another situation. You might also purposefully allocate more observations to treatments that you have more interest in, or conditions that have higher variance. And by sampling more of those, you reduce the variance of your estimate of the mean, and so you can make better inference in that way. So there's lots of reasons to have an unbalanced design, and with unbalanced designs, we're going to have types 1 and 3 sums of squares, which we'll discuss in a moment. Those will differ, and as will the averages or the estimates of the effects given in different ways. And the punchline to all this is always use type 3 sums of squares with LS means, because that will give you the correct comparisons that you want. All right, let's talk about rats and insulin. So we are conducting, in this example, conducting an experiment to measure the insulin levels in rats a certain length of time after you give each rat a fixed dose of insulin injected of one or two different ways, either through the jugular vein or the portal vein. And after looking for a long time, I couldn't find an image that had both the jugular and the portal veins labeled, but they are two different veins inside of rats. If you want to look at a bunch of gross pictures of rats with their chests peeled open, you can look for images yourself. But it's enough to know that those are two veins. It's returning blood back to the heart, and they're relatively easy to get to for this type of injection. And so once we inject a rat, we're going to wait, and in fact this is sort of an unusual experiment. We might expect to, we're going to look at 3 different time levels. We might expect that we inject a rat, take a measurement at time point 0, then wait 30 minutes, take a second measurement, wait 30 more minutes to 1 hour, and take a third measurement. But we're not taking those longitudinal or repeated measures on each rat. Instead, we inject all the rats, and then some of them are measured at time 0. Another distinct set are measured at time 30, and then the remaining are measured at time 60. So these are distinct rats. So that's what this comment is being there. If all 3 measurements were taken on the same rat, we would need a different statistical model, because these measurements would be correlated with each other over time within each rat. So, and that is called a repeated measures model. All right, So let's take a look at the data. We're going to read this off the website, and the times are numeric, but we're going to treat them as factor variables. And this is another situation, just as the battery example beforehand, where we have these times 0, 30, 60. They're numeric. Do we want to treat them as factors, as different categories, or do we want to treat it continuously? And so we don't necessarily know how the insulin is going to change from time 0, 30 to 60, whether it's going to strictly increase or whether it's going to decrease or sort of go up or down. And so it may be simpler initially just to treat them as categories unless we have an actual physical model that makes some curved, some functional prediction as to what the insulin level should be over time, having to do with metabolism and all the stuff the body does. All right, so we've got a data frame now that has veins, which are J or P for jugular and portal. We have the 3 times, and then we have insulin numbers. So let's calculate. Let's see, those are just the head and tail of the data set. Let's make some plots. So we've got insulin as the y variable, time as the x-axis, and then the color will be one or two, the 2 veins, jugular and portal, and we'll create some box plots. Let's just jump down and take a look at that one on the left. So there's the times, insulin, and the vein. And one observation to make is the jugular vein seems to have less insulin measured than the portal vein, but they both start low at 0, they increase to 30, and then they decrease a little bit at 60. That's sort of the general pattern, and it sort of looks like it's the same pattern for both veins. There's some extreme observations. Let me scroll up a little bit. Actually, let's look at the plot, and then we'll go back to the code that created it. On the right-hand side, we're concerned because this is another situation where we're starting at 0 and going positive. So we could expect here that variance and the mean and the variance are related. And in fact, that's sort of what we observe a little bit. So we have the low values have the least variance, but the higher values have more variance. And when we look at the mean on the horizontal axis and the standard deviation on the vertical axis, we do see this sort of linear trend, roughly, except for this one point. And I've got times as different shapes, veins as the 2 different colors, and I have added a number above each of the points, which is actually the sample size. So we see along the diagonal where we've got 10, 12 points, 12 points, 6, and 5. When we have higher sample sizes, both the mean and the standard deviation are better estimated, and those sort of have that positive trend. This point up here only has 3 observations. So neither the mean nor the standard deviation is estimated very well. And so that it's so unusual may in part be due to the small sample size. So I'm in my mind, I'm balancing how unusual this point is with the fact that there's a lot of uncertainty about the mean and standard deviation for that point. So I'm going to scroll up for a moment, and so the way I created this plot is we've seen this code before using plier, ddply. For each time vein combination, I calculated the mean, standard deviation, but here I've added n, which is the sample size, the length of the data frame for each subset, and so here are the sample sizes. So I've just, in the plot, here we are, sorry about the jumping around, we have a label equals n, and I've added, in addition to plotting the points, I've also plotting text, and this horizontal and vertical adjustment that I'm doing centers the numbers above the points. And I probably could have increased the vertical adjustment a little bit too, so it doesn't overlap with the shape there. So there's suggestions earlier in the chapter about how to correct this sort of problem. This is, if we just ignore this one square point with 3 observations, this is roughly linear. And the suggestion back then was to consider a log transformation. And I happen to do log on the natural scale here. It never matters what base you take the logarithm to in terms of what the effect is going to be. All that depends on is the scale in how you interpret the powers of e or the powers of 10 for the axis. So statisticians love natural log. I love natural log too, though I will admit that I also like log base 10 because it is a little bit easier to interpret powers of 10. So I've created this new variable, log insulin, where the previous one was just insulin, and now I'm just going to use log insulin instead. All right, so let's take a look at the same plots, but using log insulin. So in terms of spread, this looks pretty similar over these 4 groups. On the right-hand side, we've calculated the mean, the standard deviation, and the sample size for the log insulin. And now we see basically a horizontal pattern here, recognizing that the 3 observation one is unusual, but possibly poorly estimated because of the small sample size. All right. So we have a transformation that we think might work in terms of performing an analysis that meets the assumption of constant variance. All right, I'm going to take a tangent and then come back to the analysis of this data in a minute. So I want to talk about types 1 and 3 sums of squares. These types are named by SAS, another statistical software company, a company that actually writes very good software. It has its own syntax. For decades, the FDA, the Federal Drug Administration, accepted clinical trials only done in SAS because SAS has a very high quality control procedures for their software. One of the risks of using R, which is open source, is that there is not the same degree of quality control. I've written 3 statistical packages in R, and no one's really checking that except for me, unless someone else finds an error or a bug, and then they send me an email, and then I fix it. But on the other hand, there are lots and lots of people using R, and there's people often do check things, So anyway, just something to be aware of. Different softwares have different strategies for development. All right, so type 1 is what's called sequential sums of squares, and type 3, I don't have a name for that, but it's basically type 3 is the one we want, which has to do with conditional on all the others. What's the sums of squares for the last one? All right, let me scroll down a little bit and show you an example. So here I'm going to fit the log insulin from the data we just were looking at for the interaction model time times vein, crossed with vein. So we have main effects and the interaction. And I type this here as a big comment to let you know that we have an unbalanced design. If we calculate contrasts, in fact these contrasts right here, and perform these statistical tests, that we will have mistakes. So, and this link has a really nice discussion of why this is the case. And all I'll say is that we'll use type 3 sums of squares and LS means, and everything will work out just fine. All right? All right. So I'm initially going to show you sort of the wrong way to do things so that we can see the right way. So summary of the ANOVA object by itself will give you, by default, the type 1 sums of squares. So type 1 sums of squares is sequential. So that means that time appears first in this case, and so this sums of squares is how much variability does time account for over and above just the intercept or the grand mean. Okay? Then after time is in the model, we add vein. So vein is asking what's the sums of squares accounted for by vein after already accounting for time. Finally, the intercept, which is down here, is what's the sums of squares accounted for after having accounted for time and vein. So it's like you start with an empty model with just the grand mean, and then you add one term at a time and ask what's the additional variability accounted for by each variable. That's the sequential type 1 sums of squares. We typically don't, this typically isn't the way we want to think about things, because why should we add time and then vein in that order? Typically we want to ask the question, what's the sums of squares for time conditional on everything else being in the model? And that is what type 3 sums of squares does. So just to draw a parallel here, if we can fit enough on the screen, let's work backwards for a moment. Make this a little bit smaller. All right. So let's work backwards. So we have the residuals, which have 9.4 is the sums of squares. And that's the same as, here we go, 9.4 for the sums of squares of the residuals. Now, time by vein is what's added last. That's 0.26. Time by vein, 0.26. That's what's added last. Here's where things get different. Type 3 sums of squares down here is asking what's the sums of squares accounted for by vein after accounting for everything else in the model, which includes time and the time by vein interaction. Okay, so that's 9.13. Up here, vein was sequential. In this model, we have 9.3, right, which is different than 9.13. And this is asking what's being accounted for when only time is in the model, right? Because this is sequential up here. Time by vein isn't in the model yet. So that's why those are different. And finally, time down here is asking what's the variability accounted for by time after accounting for both vein and the time by vein interaction. That's only 6. Whereas up here, time was the first thing added, and it's 5. So just some minor differences in terms of numbers in this example, but major differences in terms of how you interpret it, of course. All right, so let's take a look. Oh, I guess we can interpret some of this stuff. Time by vein interaction, not significant. So it looks like we can probably drop that interaction, and we have the two main effects left over. All right, so create some plots we've seen lots of before, and looks like for the two vein types, jugular and portal, the log insulin on the vertical axis, we've got time on the horizontal. Basically, they both go up steeply and then come down shallowly. Probably there's this, right, we're injecting insulin, it gets, it's in the bloodstream, it increases a bit from our injection, and then the body deals with it and it decreases towards the baseline level again. That's the story that I understand from the plot on the left, not knowing a lot about rats or insulin. All right. So the means versus LS means. So LS means is going to average over the cells of the table correctly, whereas just taking the grand mean of all the observations will give us a different value when our sample sizes are different. In particular, let's take a look at the jugular values for times 0, 30, and 60. Here's the three averages at those 3 times for the jugular. And if we average those 3 numbers, divided by 3, that we get 3.74. And that's the appropriate thing to do because we want to know, on average, what is the response for the jugular vein. We have different sample sizes for these 3 groups. However, we don't want having, so here are the sample sizes for these 3 groups, 5, 6, and 3. If we just take the grand mean of these, then 60 is underweighted, right? It's sort of underrepresented. And so we're getting most of the information from 0 and 30. And we really want a balanced picture. So that's why this is the appropriate thing. If you just take the grand mean here, 3.78, even though these numbers are very similar in this case, it's not the appropriate mean, and in many examples these numbers could be very different in general. So let's take just a quick look at that. Here I'm going to calculate the mean log insulin over time. Let's see. All right, so at time 0, we have 3.99, and that's averaging over the jugular and the portal vein. And if we use LS means to calculate that, which will do it correctly, we get 3.75. Okay, so it ignores the effective sample size and just calculates the average over the 2 cells. Similarly, 4.77 is different than 4.67, and 4.58 is different from 5.27. All right. You knew that those different numbers were not equal, but there we are. All right. And so we can see that also if we compare it by veins. Okay, 3.77 is different from 3.74. And you can see if you compute things appropriately that we get the right number, 3.74, which is the same as what LS means gives us. Okay. Okay, so all of this stuff here is, actually it may not be that important. Here's the residual plots for the full interaction model where the intercept is in there but not significant. And let's see how we do. We got, see this group right here is the one with 3 observations with the large variability, large standard deviation. The standard deviation is particularly pronounced here because the denominator in standard deviation, right, it's the square root of sums of squares in the numerator divided by n minus 1. We only have 3 observations, so this denominator is 2, whereas these other denominators are 4 and 6 and so on. And so that's why one of the reasons we're getting such a large variance. It's the most spread out of any group, but also the small sample size. And observations 13 and 12, those are these 2 right here. So they seem influential, certainly because if you remove either one of them, the mean changes dramatically, but it is in the group with the smallest sample size. So I'm not actually that concerned about these 2 observations being influential, in particular because they balance each other off. One is high and one is low. So, all right, residuals look really good in terms of normality and equivariance over the groups, generally speaking. And all of this is to say that we should use type 3 sums of squares and we should use LS means. Okay. So we've got only one more video, and it's probably the most important one of all of this, which is about how to write down these equations and interpret the model coefficients. So come on back.